Hitchiner has developed and put into production a process called countergravity low-pressure air melt, or CLA. The driving force behind this development was economics. However, a solid body of evidence has been generated to show that this process yields parts that are substantially better in quality than corresponding parts using the best gravity pouring procedures. In the CLA process, the mold is placed in a vacuum chamber with an open fill pipe facing down. The chamber is sealed and lowered until the fill pipe is immersed a precise distance into the melt. Vacuum is created, which siphons the metal up into the sprue cavity, filling every section completely. As soon as metal rises above one level of gates, the full vacuum is available to fill that level, providing uniform fill-out of all parts in the sprue. CLA offers a controlled rate of mold filling at metal temperatures 200 to 300 degrees Fahrenheit lower than those required by gravity pouring, and with lower mold temperatures as well. Lower temperatures results in finer grain structure and improved mechanical properties. After a brief hold time has elapsed, allowing the parts and a portion of the gates to solidify, the vacuum is released, allowing residual metal in the central sprue to flow back into the melt. Only a short gate stub remains on the casting to be removed by a mass production cutoff machine. As a result, 60 to 94% of the metal cast is used to produce the product, as opposed to 15 to 50% in gravity poured parts, where much of the cast weight is in the sprue and gating. Unlike gravity poured parts, which must be cut away from the central sprue, there is no need to leave room for the cutoff blade in the design of a CLA casting cluster. As a result, many more patterns can be assembled on a CLA sprue. The increase in pattern population per sprue may be 2 or 3 times greater than conventional assemblies, depending on part size and configuration. The ability of CLA to dramatically reduce inclusions caused by metal turbulence is easily demonstrated by a simple experiment. In slow motion, the effects of splatter and turbulence and the mixing of air in a poured liquid are obvious. Now compare the results when the liquid is siphoned. The advantage of CLA in controlling fluid flow is apparent. CLA produces castings with far less slag and non-metallic inclusions, since the sprue is filled in a non-turbulent fashion from clean metal beneath the surface of the melt. Typically, countergravity cast metal contains only 15% of the inclusions of poured metal of the same analysis. This cleaner metal has been shown to reduce tool wear in comparative machining tests done under controlled conditions, giving increases in the life of cutting tools from 100% to 500% depending on the alloy. Inclusions are not merely nuisances for production to battle. They can cause premature part failure by serving as sites for initiation of fatigue cracks in highly stressed parts, even though they may not be detected visually after processing. The basic CLA process has, in the years since its development, lent itself to many adaptations designed for specific applications. The countergravity low-pressure vacuum process, CLV, employed by Hitchiner's gas turbine division, applies countergravity casting technology to reactive alloys that must be cast in an inert or vacuum atmosphere. Briefly, metal is melted in a vacuum in the lower chamber of the casting machine. The hot mold is introduced in a separate upper chamber, and a vacuum is created there. Both chambers are backfilled with argon. A valve is opened and the melt is raised until the snout of the sprue enters the molten metal. Additional vacuum is applied to the upper chamber to draw the metal up. The vacuum is released after the parts and gates have solidified. Hitchiner's countergravity processes provide the ability to cast sections as thin as 15 thousandths of an inch, about half the thickness of a plastic credit card. The wax patterns for these aerospace components cast using our CLV process are so thin that type can be read through them. Countergravity casting has been integrated with full automation at Hitchiner's Ferris division in the form of a multi-station computerized rotary casting machine. Utilizing a patented supported shell version of CLA, this new generation casting machine dramatically increases production throughput and efficiency. In this process, the mold is enclosed in a chamber. The chamber is raised to a sand filling valve, which loads dry sand around the hot shell. Supporting the mold with sand allows a reduction in shell layers and inhibits mold failure. When the sand is at the correct height, the valve closes. The chamber is rotated to the casting station. A vacuum head is inserted into the casting chamber compressing the sand. The chamber is lowered until an automatic sensor indicates that the fill tube is submerged in the melt to the optimum depth. Vacuum is applied, rigidizing the sand and drawing metal up into the mold. After the dwell time has elapsed, the vacuum is released, returning the metal in the central sprue to the melt. The chamber is raised, the vacuum head returns to its rest position, and the cast mold is moved to the discharge station. As this is done, other chambers are moved to the loading and casting stations. When the mold is discharged, the sand is separated from the shell and is recycled. This fully automated system provides absolute control over time, temperature, and fluid flow, achieving previously unattainable levels of casting quality. These accomplishments, and many others like them, offer dramatic testimony to the superiority of Hitchiner technology in the metal casting industry. Whether inventing new methods of casting or computerizing the shop floor, we are continually striving for new and better ways to create the best possible product. In markets ranging from aerospace and automotive to hand tools and sporting goods, the Hitchiner advantage is our ongoing commitment to improving systems, techniques, efficiency, and quality.